It's my great pleasure to introduce Jonathan Protzenko. We have this incredible project here at MSR in Redmond called Everest, and he's going to talk today about some of the progress they've made, especially thinking about the realities of program verification at scale.
Thanks, Ben, for the introduction. So the first thing that I want to say before I get started is that Everest is a pretty large project that's bringing together not only Microsoft Research, but also different academic institutions such as INRIA and CMU. So we are very distributed. There's people in several Microsoft Research all across the world. And there's many familiar faces from Project Everest that are in this room. So you're welcome to go ask them questions after the talk if you'd like to. So this talk is called Project Everest Theory Meets Reality, and that's basically going to be the two halves of my talk. I'm going to give you maybe a high-level vision of what we're trying to achieve, give you some insights about the techniques that we've developed, and that's the image that we usually put at the beginning of our presentations. And the second half of this talk is going to be more concerned with the reality, which is sometimes more like Everest scaffolding company. And we're not to the point where we've said ciao and we've gone away, but so that will be the image for the second half of my talk. So the first thing that I want to tell you about is maybe give you a panorama of the verification challenges that are present in the HTTPS ecosystem. So Project Everest is all about delivering verified components of the secure internet ecosystem. And that's where the acronym stems from. Everest really means Expedition for a Verified Secure Transport. And there's two big acronyms that we're focusing on these days, and these are TLS and QUIC. And the HTTPS ecosystem is very abstract, so I'm just going to give you a quick tour of what I mean by this. So first of all, a very, very gross approximation of what TLS is. TLS is the protocol that powers HTTPS. So when you go onto Amazon and you establish a secure connection, you're actually talking to the other party, you're negotiating some cryptographic parameters, some algorithms, some cipher suites, and that would be the first half of TLS, perhaps the protocol layer, and then there's another layer called the record layer that's specifically concerned about encrypting the data stream. So that is a very gross approximation of what's happening. And another thing that has come up recently is a very new, interesting protocol called QUIC that has been supported by various institutions, including Google and other companies, and that aims to improve by building upon TLS. QUIC is essentially about reusing the TLS handshake to negotiate the parameters and agree on cipher suites, algorithms, key exchanges. And then when it comes to transmitting the data, QUIC does its own thing using UDP for faster transmission speeds and also multiplexing the streams. So these are the two main protocols these days of the HTTPS ecosystem. TLS, the old one that you're using right now, and QUIC, the new one that's being developed by reusing a large chunk of TLS. And the question that I would like to answer in these first few minutes is, why is it hard? Where are the verification challenges in the HTTPS ecosystem? And the first one that's fairly easy to explain is when you look at the very bottom and when you're doing really core cryptographic algorithms, there are a lot of bugs in these algorithms. So there's bugs not only about functional correctness, but also about sidechannel resistance. And the reason why there are bugs is that the core cryptographic algorithms are critical for speed and performance, and people really optimize these very much. It's a lot of math, it's a lot of big num arithmetic, and because the search space is so big, it's hard to very exhaustively test these. So there's been a series of very publicized implementation bugs in places like OpenSSL, where people were really doing super hardcore optimizations over their algorithms, and the algorithm produces either the wrong result or does a buffer overflow. So these are a reality of cryptography. Another area in this ecosystem where verification is hard is when you take these crypto algorithms and you combine them to obtain a high-level construction that gives you, for instance, authenticated encryption with additional data. This is something where you have to combine possibly multiple algorithms, and you have to reason about the combination of these algorithms to maintain upper bounds on the strength of your cryptographic algorithms. So here it's a slightly different kind of theorem that you want to prove. You want to prove that your cryptographic construction preserves integrity, authenticity, and confidentiality. So you're moving from very low-level verification of math primitives to a more cryptographic argument. Another thing that's in the landscape is, of course, the handshake. There's been many notorious bugs in the handshake because it's a state machine. You exchange messages, and depending on what the server tells you, you may or may not be allowed to move forward and proceed with some sort of key exchange or some other set of algorithms. And people have made the handshakes more and more complicated because they want to start transmitting data as soon as possible, possibly giving up on some guarantees such as forward secrecy. And these have technical nicknames called 0RTT and 0.5 RTT, but the complexity of the handshake also has been a large source of bugs. Another difficulty when you look at the TLS ecosystem, the HTTPS ecosystem, is that you have to parse things. You have messages that coming from the network, you have to write parsers, and these are also difficult things to get right without buffer overflows and stuff. And finally, if you want to implement a protocol such as QUIC, you end up in the realm of low-level programming where you have low-level data structures, you have concurrency, you have to interact with the operating system, and this is also fairly difficult to do. So the point that I want to carry across is really that the HTTPS ecosystem is a minefield. There's many different types of theorems that you want to prove, and for each one of them, the guarantees are slightly different and you need different verification techniques. So the status that we're at right now is that for the low-level cryptographic algorithms that I was telling you about that are essentially about performing math, we have several of them that have been verified. The record layer that creates a stream of encrypted data is also something that is verified as we stand. The handshake is underway. Parsers are nearing completion, and QUIC is also something that we'd like to verify. So this is very much a report on work in progress. Some of these areas we have reached some degree of completion, and some of them are still on the horizon. So after this perhaps big picture and overview of the landscape of HTTPS, I would like to give you an insight on the kind of verification techniques that we use and the toolchain that we've developed to try to deliver these verified components. And the best way to summarize that toolchain is through a little diagram. So the language that we use for most of our code is called FStar. Some of you may have heard about it. It is a programming language inspired by ML, and that is oriented towards program verification. It has a weakest precondition calculus, an effect system, and uses SMT solving to discharge proof obligations to Z3. FStar is a general purpose language. It's just like in ML. You can write sets, lists, very high-level data structures. Everything is allowed. What we do for this project is we have carved out a subset of FStar dubbed LowStar, which is the subset of FStar that doesn't use things like closures or folds or lists, and that has a low-level, hence the name, a low-level flavor. And that low-level subset of FStar we compile to C, and that's what we give to people. We give them C components that they can readily integrate into the existing software ecosystem. The way we do it is that we have a series of formalization steps that go from a lambda calculus, a low-level lambda calculus called lambda LowStar. We have semantics preservation results to an intermediary language called C star, which we connect to CompCert's C-Lite semantics. And at this stage, we generate C source code, which you may compile with any of the commercial C compilers, but that you can also compile with a certified compiler like CompCert to get a maximum degree of safety. Just a few slides to give some insights about the design of LowStar. What LowStar is, in addition to a language subset, is a set of models that model the C memory model in FStar. So we have a memory model that talks about the stack and the heap. We have a set of libraries that talk about what it means to model an array. What is a C array, the operations that you can perform in it. You have combinator libraries if you want to express C loops. And the insight about LowStar is that only the code that executes at runtime needs to be low level. You can use all of the power of FStar for your proofs and your specifications. So really, all that matters is that once you've erased all of your proofs and reasoning and specifications, what remains is a LowStar program. So our motto really is that the code is low level, but the verification is not. And that's the general strategy that we have. We have these libraries that model low-level concepts, but we reflect them at the proof level using what we're familiar with, lists, sets, etc. I'm just going to give you an example by using Poly 1305, just to give you a flavor of this methodology. Poly 1305 is a message authentication code. It takes a key, some data, and it computes a MAC for it. And the guarantee is that the adversary has negligible probability to forge a MAC for a given piece of data. So you don't need to look very closely at this, but the essence is the MAC is formulated as a lot of math operations in a finite field. Specifically, the prime field 2 to the 1/30th minus 5, and you have to evaluate a polynomial in it. And that's the only part that matters. You have to do a bunch of math. That's all I want to say with this slide. And people want this math to go very fast, so they're not going to use like GMP to use like a big num library, because that would be too slow. What people do is that they have very honed, very optimized representations. For instance, in the case of this specific algorithm, and people devise representations for each algorithm, what they're going to say is that it takes at most 130 bits to represent an element of this prime field. And what they're going to do is they're going to spread out the bits of this element across 3 64-bit words, but they're going to leave a little bit of space so that when they are performing some operations, they're going to have a little bit of carry propagation in each limb, as it's called. And it's a neat trick. It means that when you have this sort of representation, 42 bits, 44 bits, and 44 bits, you can do a bunch of additions without having to do carry propagation. And of course, they have a super optimized way. The prime field was not chosen at random. When you're evaluating this, you realize that using modulo rules, it's actually 2 shifts and an addition for the core loop of the evaluation of this polynomial. And of course, this is where people got it all wrong, and this is where the bug reports that I was showing earlier came from. And the good thing with our methodology is that we use F star to specify this algorithm, and it fits within a buffer. You just have a let rec that tells you what it means in math land to evaluate that polynomial. You use natural numbers here, you use sequences, and you do the specification just like you would in normal F star. And when you use the toolchain, what you do is that you write a very low-level function whose specification says that it matches the previous slide, but whose body is a lot of very optimized operations: equality, masks, shifts. And what remains is a bunch of C code that you can actually put in relation with the original F star code, and that's what comes out of our toolchain. I'm about halfway, so maybe I'm not going to give too many insights about the formalization. I'm just going to go and show this slide, which is an excerpt of F star. Once again, it may be a little bit daunting, but what I want to say is that this captures what it means for a function to be C compatible. So we have a stack effect in F star, and a function that is successfully in the stack effect is a function that can be compiled to C. So we have a model of the C call stack. Each stack frame that you have is a little region, and what we say is that a function, in order to be in the stack effect, cannot allocate in any of the existing stack frames. So that means that in C you cannot allocate in any of your caller's stack frames. That's forbidden. And it says that it preserves the structure of the stack. So a function that preserves the structure of the stack and doesn't allocate in any of the existing stack frames is a function that can be successfully compiled to C. And that's the essence of LowStar. If your function verifies in F star with the stack effect, then what you get is that your function can be compiled to C. We do the same thing for buffers, and we model them with sequences. And then when you write buffer int in F star, it becomes int star in C. When you write index bi, it becomes b bracket I in C. And we capture temporal and spatial safety. We also have a little bit of sidechannel resistance throughout our toolchain, which I'm going to say a brief word about. What we do, the essence of our work, is that we have some secret type that is abstract in F star. We control the set of operations that we offer on the secret types, and we guarantee that the user cannot call any unsafe operations. So an unsafe operation would be, for instance, division. Division is not constant time. What that means is that if you have 2 operands, the time that it takes for the division to be performed depends on what your 2 operands are. And an adversary can observe that. So we don't reveal, so we have a limb type that is secret, and you don't know what it is. You can only know at the proof level that it is really a number. And by construction, what we forbid is that the programmer cannot divide limbs together, and because it's a different type, the programmer cannot use them to do an if-then else, or cannot use them as an index into an array, because it's an abstract type. And by typing, by construction, these things are forbidden. And we have a little semantics preservation theorem that says that if you model the trace events, then the program, once compiled to C, still preserves your side channel resistance. It's not foolproof. Of course, this does not rule out all side channels. We're only ruling out the most egregious type of side channels. And also, your C compiler may still, introduce a side channel bug by performing some dubious optimization. But there are other tools from other research groups that work and that do post-validation to prevent these. This translation from F-star to C is implemented by a tool that does a lot of compilation passes, and that is called Kremlin because it's an alternative to OCaml. There's ML in it. So we have done a little bit of performance evaluation, and right now we have a library for all of these cryptographic algorithms called HackleStar, and that has been integrated into the Firefox web browser, some bits of it for some of their cryptography. And this library is extremely competitive and in some cases even faster than OpenSSL. You can see on this diagram that we're much slower than OpenSSL in red, and that's because OpenSSL is using assembly. And it's hard to beat assembly when you're going to C code. So for that, we have another tool in Project Everest called VALE that is designed by Chris Oblizel here and Brian Parno at CMU. And that is all about verifying your assembly code at the level of assembly. It generates proof obligations that are discharged by either Daphne or F-star, and that allows you to go meet OpenSSL at the level of assembly while still proving that you're performing the right computation. And then you get the performance that you're expecting, and you get assembly code that is as fast as the assembly. So that's the theory. That's what we've presented. That's what we've presented on paper. That's our formalization. But there's another facet to this project, which is what happens under the hood. And that's what I'm going to talk a little bit about in the 10 minutes that I have left. So one thing that we've realized with the cryptographic algorithms is that this is wonderful. Cryptography is extremely regular. The allocation patterns are extremely codified. You get a big chunk of data as input. You have your caller that gives you write the result. And the memory allocation is almost non-existent except for some temporary buffers on the stack. The code is naturally low level because what you can do is take whatever OpenSSL code you find, you know how to write it, you take that as a starting point, and you already have your low level code. So the code is intended to be written in a low level style. But as we move beyond cryptography, well, the code becomes more complex and more high level. And what we have formalized is a really tiny lambda calculus that has booleans fixed with integer types and arrays, and that's not enough. People do not want to write in that sort of lambda calculus. So there has been a strong push to extend the tooling to support more programming patterns than what was originally modeled. And I think that's where the interesting bit comes in, right? You have a big project, you really want to have some programmer productivity, and you have to move beyond the paper formalization. Right now, the tooling is not verified. The Kremlin compiler is not verified yet. And perhaps my claim here is that there's a priority ordering, and the most pressing concern is verifying the source code, and perhaps verifying the tooling can come later. So there's a compromise here between scaling up the productivity of people who verify in F-star versus expensing some time and effort onto verifying our toolchain. So I'm going to talk a little bit about the sort of compromises that we've done. So one thing, for instance, that we have a lot of tooling support for is killing abstraction. Abstraction is wonderful for verification. I think everyone's convinced that abstraction equals good, but for performance, we really can't afford to have a lot of abstraction. So one thing that the tooling supports at various levels is recombining a lot of very modular verification into one big C file for your single algorithm. So we can take several F-star modules and recombine them into a single C translation unit, into a single C file, and even within an F-star module, a feature that we rely upon a bunch is being able to partially evaluate your F-star program so that all of your little beautiful helper functions that all have crystal clear pre and post conditions are inlined into one big monolithic function that the C compiler can optimize really hard. So that's one thing that we didn't quite capture with the formalization, but that has been very good for us. Another thing that we have added to the toolchain that was not in the original lambda calculus is support for data types. Programmers love data types. If you want to have an option, if you want to have tuples, it's really, really convenient. So Kremlin, the tool, has gained compiler support for it. They're compiled as C tagged unions. There's different compilation schemes to minimize the amount of verbosity for that. And of course, it's a huge trade-off. So sometimes you don't get the performance you would hope for because some compiler is not optimizing them really hard. ComCert, when you pass structures by value, because that's what they're compiled to, if you pass them as values, ComCert hasn't formalized what it means to pass a C struct by value. It's an unverified rewriting pass that is triggered very early in the compiler. And you may be bitten by the x86 ABA that dictates a very inefficient compilation scheme for these structures. But on the other hand, if you understand the performance trade-offs, it's really wonderful for the programmer because they can pass a pair. And if it's a small pair, say of 64-bit integers, the performance penalty is very low. So there has been a lot of tooling support for whole program monomorphization of parameterized data types, compilation of pattern matchings, implementation of the F-star recursive equality predicates. There's been many other things that we have added support for. In various orders, we have support for tab abbreviations. We have support for C loops using a specialized combinator library that gets a distinguished treatment, etc., etc. So none of this is very hard in a sense. It's just AST rewriting, and it's not as hard as verifying the source code. But it's a slippery slope. So eventually, I think we would like to verify that tooling. It's just that it's not on top of our priority list right now. And in the meanwhile, we're thinking about a mode that disables all of the cosmetic optimizations and allows you to just keep the core set of transformations that are really needed. There is hope. All the bugs we found so far were either in the formalization, in unverified code, or in compilers. And I can tell you about all of these if you ask me after the talk. So now I have about 5 minutes left, I think. So I'm just going to talk about two stories about delivering C code to the real world. And one of them is inside of Firefox. And the other one is one attempt of ours to run our TLS code inside of the Windows kernel. So we learned a lot trying to give C code to Firefox. So we were very research-oriented in saying we have a verified toolchain. You don't need to read the C code. Just trust of F-star specifications. Well, they had a lot of comments and they had a lot of things to say about the C code we gave them. So one story that I often tell is that Kremlin, when I wrote the pretty printer for C, I just took the C abstract grammar. They had a list of precedents for operators, and I wrote the pretty printer according to that. And one of their first requests was, you're not adding enough parentheses, because they had a lot of compiler warnings. And unless you happen to know the relative precedence of the bitwise OR operator and the plus, which I actually do because I wrote it, but apparently no one does, and it's normal, right? And I think I've forgotten it by now. You really want to put parentheses, and it's a very legit thing to ask. There were a lot of unused variables that stemmed from proof artifacts that were irrelevant at runtime, that were still there because there was a let binding in the original F-star source code for proof purposes. They asked for a lot of cleanup and a lot of honing of the generated C code, so all of these would go. Some deeper problems that we've encountered were we were using naturally a lot of recursion because F-star functional language, better for proof. That didn't quite work super well, so we had to both rewrite the original source code a little bit to use loops and also add support in the tool to transform some tailrec functions into loops. And another interesting bit is that we were just naively assuming that we could assume a recent GCC version that had a uint128 type, and that is not a valid assumption in the real world. From the infrastructure perspective, what was really fascinating was that they were very adamant about putting all of our toolchain under their CI. So they actually took a Docker container from us, which they run as part of the Firefox CI, and they regenerate the C code. And if the C code that's generated is different from what was in the repository, then it's a test failure, meaning that if someone submits a pull request that modifies the generated C code, it will be rejected. That works because that library of cryptographic code was mostly developed at INRIA, and they have a student there that spends a significant amount of time helping them out and is repeatedly interning with them. Another experiment that we've been playing with is running some of our quick code in kernel mode. So kernel mode means that the code is statically linked into the Windows kernel and executes as part of the kernel. That may sound like a terrible idea in the first place, but on the other hand, there's a lot of benefits. So first of all, You can do all of the connection management at the level of the kernel. All the acknowledgements, the retries, and the window, and like administrative managing of streams, you can do it in the kernel, which saves you a lot of user mode, kernel mode transitions, and that's important. Quick also allows you to pool several connections into a same stream, meaning that if it's at the OS level, you can pull several connections from different applications into one stream, therefore maximizing the efficiency of your connection. Another bit that's interesting is that if your keys are kept in the OS, in the kernel memory, then it's much harder for an attacker to do a huge privilege escalation to gain access to your private connection keys. You can also make the connection part of the general I/O framework, make it look like a virtual file, which is only accessible if you're in kernel mode. And finally, if you have a device driver that needs to do a quick connection, then you don't get N-quick implementations in the kernel for N drivers. So our main problem when we tried that was to actually get the code to compile with the Microsoft compiler. There were a lot of limitations that we hadn't foreseen because most of us were testing with GCC and Clang. Things that I can mention are the fact that variable length arrays on the stack are not allowed. We were generating very high-level code that had a pretty deep nesting in terms of struct type definitions, and the MSVC compiler had a hard-coded limit on how deep you can nest C structures. And finally, we found that the optimizations were sometimes, in some cases, unreliable. And perhaps the most interesting bit was all the things that were not captured by the verification. So one time, we had someone come back to us not super happy because they had had a Stack Overflow. And the reason was there was some part of glue to copy one buffer to another. And of course, we wrote it like recursively because that's the natural thing to do in F-star. But of course, like the thing turned into a recursive function that was copying byte by byte and like growing the C stack until a Stack Overflow. So what we did was we rewrote the function in C using a memcopy because it was really like essential for efficiency. Eventually, in the end, what we did was we added support into Kremlin to automatically turn every instance of tail recursion into a while loop because there were too many of these lurking, and we didn't want to have a ticking time bomb that meant that someday, maybe under some circumstances, we might have a Stack Overflow. And we did find a bug in the Microsoft compiler, which is life, and everyone was unfazed and said, well, we'll just disable optimizations for this function. We found a bug in a standard library header that was also unremarkable, and someone rewrote the function. And that's just how life goes when you try to land code in that sort of environments. So I think I'm reaching the end of my allocated time. So the conclusion is the formalization was really, really half of the work. And what is important is to prioritize the verification efforts and expense them at what matters most. And right now, that would be the source code. Nothing beats good CI and testing. We have found a lot of bugs through testing, and that's actually what we do first. We always write code and prototype it without verification, convince ourselves that it's really working, and then we try to verify it. And tooling matters. Having tools that give you productivity and that take care of the mundane tasks for you really enhances the verification experience and allows us to scale up our verification effort. The thing that I want to say is that it is all open source. Everything that I talked about is on GitHub. We're really GitHub believers. We take pull requests, and we are trying to write tutorials and make the whole tool chain more accessible. So if you're interested, you're welcome to hit us up. And I hope that by now I have convinced you that this is not a personal account of the Everest disaster. Any questions?
All right. Let's thank the speaker. Okay, I think we have time for a few questions. So
you mentioned how you're really focused on in the tooling, sort of helping people be more productive right now, getting the source right, because that seems to be the highest priority. I'm just wondering, that also sounds really scary, because they're going to have features that people love and depend on, but then when you go to actually verify the tooling, those might be really hard to reason about. So I was wondering, are you taking any measures to try to upfront design that with eventual verification in mind?
Yeah, so we're trying to do things that are not too ninja. So all of that pattern matching compilation and things, all of these I can explain to you on a whiteboard in like a very short amount of time. The one optimization that I mentioned was compiling tail calls into while loops with assignments. And usually my criterion when people come to me and say, hey, I really need something in Kremlin, is can I implement it in a buffer? And so that transformation to turn tailrec calls into while loops, I can fit it in one of my screen buffers. Granted, I have a big screen, but it's not like it's a huge transformation that took me like 2 weeks to complete. I have visitors, it's a AST rewriting, so it's not super ninja. And that's usually where the criterion is when someone really comes and asks for tooling support, because of course people always want more tooling support because you want to shift the burden of verification into the tool. And the criterion is, can I explain it to someone without embarrassing myself? Is it something that I can implement trivially and that I would be able to spec easily? And that's the criterion that we have. It may sound a little bit scary, but the pattern matching compilation, for instance, is very straight line. It just compiles into a series of if-then-else. And I could show you the code and you would read it and you would get what it does. There's nothing, at no time do we do something super specific and super narrow because we think we're going to optimize. We don't do that. It's the simpler, the better. So yeah, I think when the time comes and where we're ready to verify the tooling, we will find that nothing is ninja and nothing is impossible to verify.
I really like this one screen full of text principle, right?
Yeah.
That sounds like a nice rule of thumb.
Yeah.
Other questions? One more?
Anybody?
No. So I can talk to him afterwards. Okay. So you're verifying Quick, which at least as far as I understand is still under development or still under the standardization process.
Yes.
Has any of your, and I know that you mentioned Quick is sort of still in progress, but has any of the work that you've done impacted either how the standard is being written or at least how you think it ought to be written to make verification of implementations easier?
Yes, we have an expert in Cambridge who's sitting at the standardization table for both TLS and Quick, and he participates in the discussions and informs the process. And I know that for TLS, there were implementation, amendments to the working draft that were a direct response to some suggestions made by us.
All right, let's thanks, speaker again.